So the answer has been artificial intelligence in the form of deep learning. As you all know, and you're probably seeing it everywhere, artificial intelligence in the form of deep learning, wherein software, AI writes software. In the past, humans write software. Now AI is writing software. And the way it's being done essentially is by AI reading all the different data and finding patterns in the data and then coming up with the answers. And that's what deep learning is. So this whole mobile cloud revolution that happened in the last 5 years with enormous amount of data available from all the sensors in the world, and then all the cloud revolution with GPUs powering in the cloud, combined with that, AI explosion has happened. And self-driving car is one of the big industries that deep learning is transforming. And you have to do many different things, right, in a self-driving car. The first step we need to do is perception. You got cameras. Traditionally, there used to be a front camera and maybe a rear camera. Now we have many cameras in a car. We have 6 cameras to 12 cameras in a car. Multiple front cameras, side cameras, rear cameras, different resolutions, some with longer distance, longer focal length, and some with shorter focal length. And resolutions are continuously increasing. Now 1080p, and in the future, some of these cameras will go to 4K for a fully self-driving car. So you have to, and then in addition to cameras, you have LiDAR. And then we have ultrasonic radar, and in some cases IR. So there's all these different type of sensors that are now coming into this autonomous vehicle. You have to perceive the world using all those sensors. So that's a lot of processing that we need to do. And then once you perceive it, just like a human does, we have 5 sensors. Once you sense it, you have to reason. That's where a human brain comes in. And this is where a lot of AI will come in. What is this that you want to do once you sense the world? And then once you reason, you have to basically plan and execute the plan, which is in the case of a self-driving car, it is basically deciding which path to take. So you have to predict where you want to go. And along the way, to help in that, we have HD maps. So basically knowing where you are in the physical world. So combined with all of this, there's a lot of technology that is going into the self-driving car. So as it turns out, if you think about a self-driving car, and NVIDIA, we have our platform called Drive that we are, pioneering this on with many of our partners, including Audi. There's many neural networks that are running at the same time. First of all, I talked about many sensors, right? You got 6 to 12 cameras. You got a LiDAR probably. You got radar. You maybe got IR. So you got all these sensors, number one. And then you are doing multiple networks at the same time on all those sensors, or some of those sensors. So that requires a lot of computing power. So you got to obviously do perception, you got to identify objects, detect and classify objects. Is it a person, is it a car, is it a bicycle, whatever you need to do. You need to do free space, where is the free space versus which is occupied, where the car can drive. You need to measure distance, whether that is through stereo camera or as a combination of LiDAR and radar and camera. You need to perceive the distance of the object and the trajectory. Obviously different weather conditions. It could be raining, snowing, it could be hot, it could be any of the scenarios. And then of course you got LiDAR as for redundancy and diversity. Cameras, as I mentioned, and localization to HD. So all of these things need to be running simultaneously, real time. So that requires an enormous amount of compute. So unlike in the past with ADAS, where we could add one feature at a time and incrementally add the next feature, here we are suddenly going to a completely different game where you have to do, in order to do self-driving, it turns out you have so many sensors and you need to do multiple networks at the same time. So we have Drive is NVIDIA's platform for automotive. A few years ago, we started off with Drive PX2, which was based on our previous generation Tegra SoC and discrete GPU. And then last year, we've announced our Drive Xavier, which is essentially a single chip supercomputer that can deliver 30 trillion operations per second for deep learning. And that's what will, in just one SoC. And that's what really enables level 3 and some level 4 type of cars. And then we also built a time machine, which is what our Drive Pegasus is for robot taxis. So in the case of a level 3, there is still a human-assisted driving. When you go to a robot taxi, and one of the cars that I saw earlier is where there's no steering wheel, there you're talking about the ultimate in terms of self-driving, where everything needs to be done by the machine. It has to operate in a fail-safe manner. That means in order to operate in a fail-safe manner, there's multiple things that we need to do. First of all, since there's no human in the loop, we need to have diversity and redundancy. So we need to do the same task in different ways to make sure that the answers are all correlated. So inside Xavier, we have many different engines. We have GPU-based deep learning processing, we have deep learning accelerators, we have CPU, we have vision processors, we have camera processors, and video processors. All of these together form the underlying hardware computing platform. And on top of that, first of all, we built all of that to be ASIL-D certified. Xavier is the world's first and only autonomous machine processor that has been already certified for ASIL-D. So we do all that redundancy in hardware, and then we built the software stack on top of that with redundancy as well, and diversity as well. So NVIDIA, we're building our own self-driving stack, and then our partners build the stacks, the same task done in multiple different ways. And then Pegasus is what allows us to do a fully robot taxi, and you can see the performance scaling up to 10 times. And Pegasus has 2 Xaviers and 2 of our discrete GPUs. So this one architecture allows the industry to start all the way from level 2 to level 5 and have a singular software stack. Now, the car driving itself is obviously the most important thing, and that's what we always think about. But how do you even get there? How do you, obviously you build all these networks, but how do you know that the networks are good? How do you validate those networks? And the answer, as it turns out, is you can't validate it by putting self-driving cars on the road and collecting all the data. That is absolutely necessary, but not sufficient. Just think about it. Humans, the whole world combined, approximately 10 trillion miles every year. That's how many cars and buses and shuttles and trucks are driving. How many miles do you think a self-driving car can drive in a year? 20,000, 30,000, 50,000, let's say 100,000. And how many self-driving cars are on the roads? A few thousands, maybe. So if you multiply all of that, still the cars will not have enough experience in the real world. While real-world testing is absolutely essential, it's not sufficient. It will not encounter all the corner cases. And actually, it turns out that the toughest part in self-driving is not driving right 99% of the time. I think driving right 99% of the time is not that difficult. But driving right that 1% of the time when the corner case comes is what we humans are good at. And the whole idea of this autonomous vehicle is that we want to do it better than what a human can, so that we can prevent accidents, we can reduce the cost of insurance, and we can improve the overall quality of life. So in order to do that, you need a testing validation system. So we've built this supercomputer. So earlier I mentioned that AI is about AI writing software, or software writing software essentially, versus in the past, humans write software. In the past, if you wanted to be a software company, of course, the number of software engineers dictated how much software you could output, right? Obviously the software engineer, assuming the software engineer is good, and you have many good people, you can write a lot of software. Now in the world of AI, and if AI is the software that's writing software, the answer is that how much computing do you have? How many supercomputers do you have to make this AI software write more and more software and test more and more software? So that's what it's all about. So we've created this system called the Drive Constellation, which essentially is a supercomputer with many of the GPUs inside that's constantly writing and testing software in simulation. And then, once we do that, what we do is this thing called hardware in the loop. So we can write all the software, all the networks, and simulate it in the supercomputer. And then the same networks are downloaded onto the Drive platform, which is the in-car platform. And that hardware is constantly being tested in the loop. The benefit of that is you can actually introduce all the different corner cases in the simulator. And then you can see how the car is driving. So here, let me go back and read on that again so that you can see what's happening. What's happening on the left is the simulator. And what's happening on the right is those networks essentially running on the drive platform. So it's hardware in the loop testing. So you can introduce all sorts of corner cases in the simulator and then see how the real physical car on the right-hand side is behaving. So this is called hardware in the loop testing. Because we share the same GPU architecture end-to-end, we're able to run the same neural network in simulation and in the car. Now, of course, self-driving car is about driving, but also the interface to the car is extremely important, as you've seen some of the presentations from some of the startups earlier today. So how you interface with the car is also extremely important. So there's going to be AI in the car as it interfaces with the human. That's also going to be an important piece. Obviously in terms of perceiving the environment around within the car, speech recognition, synthesis, natural language processing, eye tracking, head pose, gesture recognition. As you can imagine, the step from where we are today to a fully self-driving car is not a single jump. It's going to be done in phases. So along the way, we continually need to improve it. So AI inside the cockpit is also going to be a huge, important technology moving forward. So the infotainment that I showed you earlier, that all the cool UI, that all is going to be now transformed into mixing of AI inside the cockpit. So we have this end-to-end platform for drive, and there's 4 pieces to it. The first piece is collecting the data. So you have, hundreds of thousands and millions of miles that cars are driving along the way, right? You collect all the data. Collecting the data is not that difficult. You basically need human drivers, and you put cameras or you put the different sensors, and you just pick where you want to drive. But processing the data is a huge problem. And labeling that data is essentially very important. And we at NVIDIA actually have many hundreds of people, literally 1,000+ people doing all the labels, because it's such an important task. We want to label so accurately because this is the future of autonomous vehicles is going to depend on how good you label. We obviously use AI to assist in some of the labeling, but we label each image that we get twice. Different people, different techniques to make sure that we align on that. So the first step is collecting the data. So this involves essentially, doing all the labeling in a data factory. The second model is training the models. And training the models requires a supercomputer. As I mentioned earlier, so many networks running in parallel, you got to constantly train these models and constantly evaluate them. That requires a supercomputer. Third step is simulating those models in the virtual world. So to do that, again, you need a supercomputer because you can simulate 10 trillion miles, but you cannot drive 10 trillion miles. There's just not enough time to do that. So simulation also requires supercomputers. So the first 3 things that you see there, the collecting the data, labeling the data, training the models, and simulating the full self-driving car stack is all done on supercomputers. So this is the point about AI writing software, software writing software. It really gets down to how much computing resource do you have. And then the last step, of course, is the in-car hardware, and that's the drive platform that I showed you earlier. So we at NVIDIA are building this complete end-to-end platform, and Audi is one of our prime partners. And earlier this year at CES, actually our CEO and Audi CEO demonstrated what the future of autonomous driving is going to be. And it's definitely going to go along the lines of this. So building a full autonomous vehicle is a huge endeavor, and at NVIDIA we have several thousand people working on this, and we started this journey 7 years ago. Okay, with that, I'd like to thank you for your time.
Thank you so much.